Hey everybody, Trey here. Welcome back to another video. Back with another case study for today. We're going to talk about the destructive Joplin, Missouri EF-5 tornado from May 22nd, 2011. Some of the infamous footage from that event showing on your screen here from Jeff and Kat Petrowski. This was a deadly tornado. This single tornado killed 158 people, making it the 7th deadliest in United States history and the deadliest since 1947. So I wanted to do a deep dive into the meteorology of this event, look at some things that may have made this supercell such a powerful one. And then toward the end, we're going to look at some analogs, some setups that were similar to this one. And it turns out that this environment that fostered this tornadic supercell here in Joplin isn't all that uncommon. So we're going to talk to you about some things that you can look for when you're forecasting for severe weather that you can kind of use as pattern recognition for future events. Before we start here, I want to draw your attention to this article here by John Davies, private meteorologist out of Kansas City. We talked about his work with cold core tornadoes and tornado environments, and he does a great job with both cold core events and some of your more normal events, and this was one of his articles here in the Electronic Journal of Severe Storms Meteorology, detailing what the meteorology behind the Joplin tornado event. I'll be referring to this article sporadically throughout the video, and I'll put a link to this article in the description below if you want to read up more on the Joplin event. So, without further ado, let's go ahead and get started here. We'll talk about first, kind of give you some context about the overall event. So this was the morning outlook from the Storm Prediction Center on May 22nd. You can see a large area of moderate risk here extending from kind of northern Wisconsin down through the kind of northeast Oklahoma area. Big ol' slight risk area surrounding that. Remember, this was before the enhanced risk category was included in the SPC outlooks. We had a 15% hatched area for strong tornadoes extending from northern Wisconsin through pretty much eastern Iowa, western Illinois into northeast Missouri, with a large 10% hatched area extending down toward the Red River. Now, Joplin sits right in here, kind of at that Kansas, Oklahoma, Missouri triple point right there. And so it was well outside of the kind of greatest tornado threat in that 15% hatched area, but it was well within the 10% hatched area. And we'll talk about kind of the bimodal event that occurred here, kind of bimodal setup here in a second. We also had a damaging wind threat as well as a large hail threat that kind of most greatly centered on that sort of southwest Missouri to northeast Oklahoma corridor. So definitely was the threat for numerous supercells with significant severe weather likely throughout the region. But again, the Joplin storm was well outside of the greatest significant tornado threat. So let's start at 500 millibars as we usually do here. You can see a very well-defined closed circulation here centered across eastern South Dakota there with a nice belt of enhanced flow rounding the base of that trough. Now farther to the south here, a little bit more of a muted, more zonal sort of pattern here across that southeast Kansas, southwest Missouri, northeast Oklahoma corridor, a little bit farther removed from the actual trough here in the southern portions of the risk area. And I want you to keep an eye on both the location of Joplin, which is right in here, and this contour, this 5760 contour right in here. Now these are not isobars or lines of equal pressure. These are called lines of equal geopotential height. And geopotential height is simply the height of a given pressure surface above sea level. So if we were an observer looking dead ahead at the 500 millibar surface, you can kind of think of it as a sheet of paper. And it's going to change its height based on things like temperature if you were to look at it over a given distance. Now let's say this dashed line here is the surface. This is sea level, mean sea level here. Geopotential height is just the height of that 500 millibar surface above sea level at a given location. So what we want for severe storms typically is to see geopotential heights falling over a region. Height falls promote rising motion, which is favorable for storm initiation in a given environment. When heights rise, or when we have height rises, that promotes sinking motion and is less favorable for storm initiation in a given environment. So what I mean by height falls and rises, let's say we have a location here. This is where we are. We're sitting right at this star. And let's say we have a 500 millibar trough that's approaching. Let's say we have the 5760 contour here, and we have a 5720 contour to its west, and the trough is again moving this way. Well, at our location, over time, these height contours are going to translate this way. So let's say over a period of several hours, this 5760 contour might be over here. And now this 5720 contour might be right over us. And that means at our location, heights have fallen over time, and therefore that is favorable for rising motion and storm initiation if the ingredients are there for severe storms. That's what we want to see. Not necessarily height rises, because that promotes sinking motion and is less favorable to get storms going in a given environment. So again, keep an eye on Joplin, which is right here, and this 5760 contour here, particularly in this kind of northeast Oklahoma, southeast Kansas, southwest Missouri area. Notice that over time, as we go forward, that 5760 contour rises. It moves toward the north a little bit. So it started out here, now it's here to the north of Joplin. That means at Joplin that heights have risen throughout the morning and afternoon hours here. And again, we want to see height falls. And that's particularly a reason why the northern part of the risk area was a little bit more favorable for severe storm initiation. They had the strongest parameters up their contours up here, the SPC did. There was a little bit more of a signal for height falls and therefore storm initiation farther toward the north, up here in Wisconsin, Minnesota, Iowa, Illinois, northeast Missouri. Farther down to the south, we were seeing more neutral or rising heights. But there was a lot of features at the surface that were going to help overcome these height rises and kind of large-scale sort of subtle rising or sinking motion. And we'll look at the surface map right now to show you that we were going to be able to overcome this lack of overall large-scale ascent or synoptic scale ascent here. So 12Z, surface low, centered right here over eastern South Dakota, with an attendant cold front draped here across eastern Nebraska, eastern Kansas, down into Oklahoma. This was going to move off toward the east throughout the day, but not very fast. We've talked about storm mode and frontal forcing from the initiating boundary in determining what our storm mode is going to look like later on. And when your cold front is moving really, really fast, it's really surging, that usually means that it's a steeply sloped cold front, lots of cold air behind it, and that's going to force a lot of storms to go up along that front, and more so, you're going to have a more linear sort of organization of the storms. If your cold front is not moving all that fast, then you're not going to get that strong frontal forcing, and you will still be able to get discrete storms from a slow-moving cold front. That was the case here. And notice here by 19Z, so a couple hours after lunchtime here, our low had moved into Minnesota, with our cold front still kind of draped. It moved east a little bit here, out across southeast Kansas there, just toward the west of Joplin there. If we look at our data here at the surface, this is at 14Z. You can see where that cold front is. It's a little bit hard to tell here, but you can see that the winds are shifting. You can see pretty much westerly winds out here across northern and central Kansas, even northerly winds out here across central Kansas, shifting to kind of southwesterly flow here and then southerly flow out here in the open warm sector. So our cold front was sitting kind of somewhere, roughly speaking, kind of out in this sort of zone here at 14Z. A little bit difficult to tell, but that's kind of where our cold front was situated here, respective to our southern target here. As we moved on in time, we continue to have warm, moist advection throughout the afternoon. You can see dew points here in the almost mid-70s here across eastern Oklahoma, low 70s, upper 60s here across southwest Missouri, southeast Kansas here as storms were about to fire. And so we moved on a few hours here. Our cold front situated somewhere in here. You can see that the dew points definitely drop off here toward the west, 85 over 47 at Wichita, 81 over 70 here at Chanute, I believe, 84 over 70 here at Joplin at this time. So our cold front situated somewhere in there, warm, moist air mass out there. So this was going to help things, and you'll notice here, if you look really closely, you can see somewhat of a weak circulation here developed along that cold front. You can see that the winds out here across northern Oklahoma were out of the northwest, shifting to southwest here across central Oklahoma, then more out of the south here across northeast Oklahoma and southeast Kansas. So we had somewhat of a frontal low kind of develop right in here, and that helped increase kind of lift out ahead of this cold front kind of formed a sort of triple point here. Your dry line was focused somewhere in here, and you can just see dew points sort of bending back into the surface low up here. 72 dew point, 69 here at Tulsa, 91 over 59 here to the southwest there. So your moisture was just feeding up into that, and that created a nice triple point out here ahead of the surface low out here, the weak surface low out here across southeast Kansas that was going to help initiate storms just ahead of the cold front. Now, another thing that I want to take note of here, let's look at our satellite imagery here. So first off, we had some storms the day before. This is May 21st. We had some tornadic storms up here in northeast Kansas, and they became much more numerous after dark, and they moved off. You can see outflow pushing out from these storms here. This was over the overnight hours, outflow pushing out from these storms, and we cleared out by the morning hours. Now look at our satellite imagery here. I want you to note this band right here across northwest Missouri, and this is at 1345 Z, so this is just before 9 a.m. on May 22nd. This band was very, very noticeable in satellite imagery and moved toward the east throughout the day. And you can see it drifts off toward the east here, and then by the time of storm initiation, we had storms developing along that band in western Illinois, northeast Missouri, and then eventually down to the south here, where that cold front was just ahead of that surface low, perhaps meeting up with that outflow boundary right there in southeast Kansas. Now, it's very difficult to see on our surface map here, but let me draw our components here. So the cold front situated somewhere in here, our dry line somewhere in here, and our surface low, very weak surface low, somewhere right in there. Now, I want you to look at western Illinois and eastern Missouri here. You can see a very subtle wind shift here, kind of a southwesterly wind right there at a UIN, shifting to southerly winds here across western Illinois. We continue to see that as we go into Missouri. Columbia here, southwest wind, VIH, not 100% sure what that is, but winds are out of the due south there. And that continues down into southwest Missouri. So it does appear that this was some sort of outflow boundary / gravity wave here extending into southwest Missouri. Now, you can't really make anything out ahead here in southeast Kansas to southwest Missouri. So the jury's still out whether or not this boundary actually was extending back here into far southeast Kansas, far southwest Missouri in the vicinity of Joplin. But it does appear that there was a mesoscale outflow boundary there, and the SPC even mentioned it in their mesoscale discussion here. Their first discussion highlighting the potential for this area denotes the location of this gravity wave right here. And the gravity wave is just a fancy term, fancy way to say a wave. And all a gravity wave is when air is forced upward in a stable part of the atmosphere. So basically, when you have thunderstorm anvils trying to push up into the tropopause, which is a stable layer right there, they are going to often create gravity waves as they try to do so. And this gravity wave was likely the result, that gravity wave / outflow boundary, likely the result of overnight convection there. We saw on our radar imagery, we had lots of overnight convection there. Still not 100% certain though, because if you see the outflow boundary does move well off out here toward the east here, and it's kind of cleared the picture by the morning hours. And if we look at our satellite image here, 1345Z, our gravity wave looks like it's right in there somewhere, whereas it should kind of be off here. So not sure if it's directly related to these thunderstorms here that were taking place overnight here across Missouri into Iowa and Illinois. But it does look like there was a gravity wave / mesoscale outflow boundary there that did extend into southwest Missouri. Again, whether or not it extended far back here to the southwest into southeast Kansas, southwest Missouri, still in question, but it very well may have, and may have fostered a little bit of a localized enhancement of vorticity along it, and may have helped out the Joplin supercell as well. Just wrapping up the overall meteorology here, so that's kind of our setup here. So pretty interesting setup here, kind of twofold, sort of bifurcated sort of surface low situation here. We had our main surface low well off to the north, cold front sagging down to the south here across southeast Kansas into Oklahoma, with kind of a secondary low, kind of your dry line feeding up into that secondary surface low right there in far southeast Kansas. And keep this in mind for later on. We're going to go through some analogs, and I'll show you some setups that are very well-known tornado producers that had a very similar setup to this. So we'll look at that toward the end of the video. Just to wrap up the meteorology here, let's go down to 850 millibars and show you what was going on here. Very nice low-level jet in place here. This was the 18Z map here, so 1 p.m. Central Daylight Time here. Nice south-southwesterly low-level jet here, feeding up into that surface low, or that low-level circulation up there across eastern South Dakota into Minnesota. 30, 40, 45 knots here of moist southwesterly flow, really pumping that moisture toward the north here up into the region out to the east of that cold front. Now, at first glance, you might say, well, this low-level jet is pretty veered. Shouldn't that kind of negate the tornado threat? That's not always the case. Yes, we do have to keep in mind that if we do have a southwesterly low-level jet, it may start to bring some of this dry air out here from the desert southwest and western Mexico up into the low levels, and that may have an impact on things. But we do have a nice reservoir of moisture up here into far kind of southwest Texas, and that was getting pulled northward along this southwesterly low-level jet axis. So not too much of a concern there. As far as the wind profiles go, that may be a concern, but our surface winds out here in the region were kind of south-southwesterly, almost due southerly across this region. So if you have south-southwesterly surface flow and southwesterly low-level jet, low-level winds that increase there, that's going to create enough shear for tornadic supercells there, given all the other ingredients are in place. So that wasn't too much of a concern there. And let's look at some soundings to kind of confirm that here. This is the 12Z Springfield sounding. Now, this was the old SPC sounding viewer. I was not able to pull a 12Z sounding here from Springfield using our SharpEye format, but this will do. So this was our 12Z sounding at Springfield, just off to the east a little bit from Joplin. Fairly nice proximity sounding here. So you'll notice a couple things going on here. A little bit of a moist layer there, up just below 850 millibars. Not extremely deep there. A very stout elevated mix layer, though, in place there. Of course, we've talked about the elevated mix layer ad nauseum here on the channel. That EML is that layer of dry, warm air, steep lapse rates aloft that starts out in the desert southwest and gets transported off toward the east, just above that surface moist layer out in the southern plains, or wherever our severe weather setup is taking place. And we had a very stout elevated mix layer here. You can see this layer here across from 850 millibars up to about 600 millibars or so. Very steep lapse rates in this layer, creating a very stout cap that was in place for much of the afternoon. Now, given the lack of overall synoptic scale forcing, remember we said height rises were kind of taking place across the region, this cap was a little bit questionable whether or not this would break, but we had extreme instability in place. This is the 18Z sounding here at Springfield. You'll notice here that cap's still in place, elevated mix layer there still in place. You can see 9.3 degrees Celsius through that layer, degrees Celsius per kilometer through that layer. That is extremely steep lapse rates there. So very stout EML, but we did have enough forcing from the various mesoscale kind of surface boundaries there, enough forcing from those boundaries to help eliminate that cap, and quite a bit of surface heating. If you recall our satellite imagery, very clear through much of the afternoon, some broken high clouds there across the region, so surface heating was not really an issue for the southwest Missouri area. Moist layer had deepened by 18Z here, 1 p.m. Central Daylight Time. It extends up above 850 millibars now, so we'd had that continued moistening of the low levels. And then by 0Z here, you'll notice that cap completely gone and just extreme instability in place. This was the observed Springfield sounding again, 4,800 joules per kilogram of mixed layer CAPE. That is just absolutely off the charts there. Extreme instability in place. Ample low-level shear here. You can see despite the south-southwesterly surface winds and southwesterly low-level jet, we had plenty of turning in the low levels. Lots of streamwise vorticity here in the low levels here. Nice curvature to the low-level hodograph there. And so it was very favorable for tornadic supercells in this environment. We'll look at some RUC soundings. The RUC was the rapid update cycle, basically the old equivalent of the current RAP model. And this kind of shows it better, what happened to the cap throughout the afternoon. So this was at 17Z, about noon on May 22nd. You can see that cap's still there, very strong elevated mix layer there above a nice, fairly deep surface, low-level moist layer. Already a very favorable looking hodograph there. Fairly weak winds aloft here. And you can see our storm motion is right there. Very kind of limited storm relative outflow there. In other words, the 6-kilometer winds, not that much different. The winds around and above 6 kilometers were not that much different from our storm motion vector. There wasn't a lot of distance between the two. That's kind of a layman's way of saying that the storm relative outflow, at least above 6 kilometers, was fairly weak. So that was a sign that we may be seeing some high precipitation supercells. Oftentimes for a more classic or low precipitation storm mode, you'd want those upper level winds to really be quite strong and to help vent that precipitation off away from the mesocyclone region. And that was not really the case here looking at these rapid update cycle models. Now back to the capping inversion here. Notice our cap's still in place here at 17Z, and notice what happens by 21Z. That cap has been lifted and cooled, and we've talked about this in previous videos. This is how you erode the cap. When you have forcing from various mesoscale boundaries, a trough coming in, that cap is going to get lifted up in the atmosphere and cooled, and that's how you erode the cap. And by 21Z, we were fully eroded here. Very steep lapse rates aloft, extreme instability over 4,000 joules per kilogram of mixed layer CAPE, low-level instability very strong at 114 joules per kilogram. And this again, this is at Joplin here, a RUC model sounding. So this was an atmosphere that was extremely primed for tornadic supercells here. You can see that the moist layer had continued to deepen as well. 82 over 71 here at Joplin. Very large looping hodographs here in the low levels, ample streamwise vorticity. Again, that's the comparison of the storm relative wind vector and our horizontal vorticity vector, which is perpendicular to the hodograph. When those are parallel, you have lots of streamwise vorticity, which is favorable for tornadic production in supercells, and we had a lot of that here. So the atmosphere was extremely primed for tornadic supercells. Perhaps some high precipitation nature to the supercells, given the limited sort of storm relative outflow there. So that was a concern as far as storm visibility went. And that would become a concern later on with the Joplin supercell. So let's go on and look at our radar here. So we'll look at our reflectivity to start here. So again, Joplin is right in here. Here's our Springfield radar site. And you can see here early on that storms were going to fire kind of along that cold front. Remember, our cold front located kind of right in here. Weak surface low sort of right in here at the Kansas-Oklahoma border. And that was kind of our sort of triple point area right in here, and these storms were able to form right along that sort of triple point area. So we go on with time, and we quickly get sort of a clustered storm mode. We do have kind of semi-discrete elements up along the line. However, in this particular region, storms started to cluster fairly quickly, and so that was a concern right away that the storm mode may not be super favorable for tornadoes moving forward. So we go on with time. You can see here it's just kind of a blob. We had an embedded mesocyclone within this cluster here. Here's our velocity imagery. You can see it quickly develops sort of a low-level mesocyclone there within that sort of cluster. But it was going to be hard to sustain that given the overall storm mode here. Just very, very clustered, multiple updrafts here competing for the ingredients in the environment. And we started to see some shower development. Here, this is at just after 21Z, so just after 4 p.m. here, we started to see some showers develop out to the south of the ongoing cluster of storms. And these two in particular started to become more robust. You can see kind of, we start to get sort of, semi-discrete elements out here in this main cluster. So you had kind of your main supercell, your lead supercell out here of this cluster. And then you had these two sort of developing supercells out here toward the south. We'll call this storm A and B. And John Davies uses this nomenclature in his article here. We'll call this storm A and storm B here. So we continue to go on with time. And you can see that storm A starts to merge with the ongoing supercell up here toward the north. And storm B starts to develop its own mesocyclone and hook echo. We'll zoom in here. And this is at 22Z, so 5 p.m. And again, here is Joplin right in here. And so Storm B started to develop its own hook echo here. You can see it started to wrap up there. Storm A had started to merge with the storm toward the ongoing supercell toward the north. And over time, this was a new storm that started to develop toward the south. Storm B merges with Storm A and the ongoing sort of storm cluster that Storm A had already merged into. Then we get this kind of conglomeration here where Storm C starts to impede with the inflow region of the ongoing sort of supercell cluster there. And then we get tornadogenesis there right on the east side of the Kansas-Missouri border. As those two merge, Storm C merges with that ongoing cluster. Then we get our hook echo there right just east of the Kansas-Missouri border. And then we quickly develop a debris ball there. You can see just an absolutely horrific looking radar image when you have a populated area that this is going through. Debris ball there. We'll go to the velocity data real quick. Let me look at our zoomed in velocity data here. So you can see the ongoing storms had kind of a mesocyclone there. That was the southernmost storm, Storm C. So our ongoing cluster was up in there. And then we got kind of conglomeration of those two and a tornadogenesis there just on the east side of the Kansas-Missouri border. And that quickly intensified and moved through the Joplin area and created that very strong velocity couplet and very just incredible looking debris ball there as it was producing EF-4 and EF-5 damage going through the heart of Joplin, specifically near the medical center. Now, we already established that there was going to be more of a tendency for these storms to be more of a high precipitation sort of mode. And that was kind of amplified by the fact that we had storms kind of continue to go up and kind of stay in the sort of hook area of the supercell. So that further impeded the visibility with this storm. That likely was an added factor to such a high death toll with this storm. Is that the tornado overall was very, very rain-wrapped. Unless you were very, very close to it, as we saw in Jeff and Kat Petrowski's footage there at the start of the video, that unless you were very, very close to it, kind of in the bear's cage right out ahead of it, that you were really not going to be able to see this tornado. It was going to be very shrouded in rain, both given that the precipitation here, you can see it's being vented out ahead of the mesocyclone and area of the tornado, and also these storms were hanging out just in the and kind of coinciding with that mesocyclone region of the Joplin storm, making it even harder to identify, at least from a great distance. So this was likely a very hard tornado to spot if you were at any distance from it until it was kind of on your doorstep. And of course, we know that people like to get visual confirmation when they hear a tornado warning is issued for their area. So they likely stepped outside, and perhaps it was right on their doorstep, and it was too late, and they could only start to see it when it was right on top of them. So that just added to the volatility of this storm. We move on with time here. Debris ball just grows. I mean, that's just an awful image. I remember at the time looking at this radar imagery as this was ongoing and just seeing this debris ball there and just super intense couplet there going through the heart of Joplin. And it was kind of a heart-wrenching moment there. Tornado moves off toward the southeast there and dissipates with time and kind of just clusters out there. Very large cluster of storms there. We'll zoom back out, kind of give you a zoomed out view. So this, again, we have possibly our outflow boundary, our gravity wave extending back here into southwest Missouri ahead of these storms that may have helped out to enhance the low-level vorticity out ahead of this storm. But also storm mergers played a huge role in the intensification of this storm. We've talked about storm mergers before, including in our last video on the recent Texas tornado event, that you can have one of two things happen when you have storm mergers. You can have constructive interference, which is where the storm will merge with an ongoing supercell, and then you will get a ramp up in tornado production. It kind of becomes one main supercell, and you'll often see a ramp up in tornado production as a result. You can also have destructive interference, where you have storm mergers, maybe too many storms near one another, crashing into each other, and those storms will just kind of cluster out, and the tornado potential will decrease, and the overall severe potential as a whole may decrease as well. And in this case, we had very constructive interference with this storm. You can see that the main sort of kind of secondary storm here, we called this Storm B, that started to develop its own mesocyclone here to the south of the ongoing supercell cluster, which Storm A had merged into. So Storm B was already a legitimate supercell here, and we got a merger between Storm B and Storm A's sort of complex, and this kind of tertiary storm, Storm C down here, and they eventually merged and kind of became one supercell here, and that quickly ramped up the tornado potential down here with this Joplin supercell pretty quickly once it crossed the Kansas-Missouri border. So storm mergers played a very critical part in this, in the powerful nature of the Joplin tornadic supercell here. And again, we could have had some external influences from that outflow boundary / gravity wave there. Again, the jury's still out on that. There is some evidence that it may have extended back here into southwest Missouri, but it's a little bit muddy whether that was actually the case. But that was the main thing that amplified the tornado threat with the Joplin storm were those storm mergers, and then a kind of dominant supercell taking over and taking advantage of such an explosive environment such as this one. Huge instability, huge low-level instability, ample low-level shear and streamwise vorticity to feed that supercell, and that's what made that Joplin storm so powerful. All right, let's kind of close things out here by taking a look at some analogs, and these will definitely be analogs that you've heard of. And John Davies outlines this in his paper here, that this kind of setup is not as uncommon as it might seem. So I want to draw your attention here to figure 13 here. And this was kind of a schematic diagram that Davies constructed here to kind of give us a sense of what goes on in these setups. And it's exactly what we saw when we looked at our surface data. We have our primary surface low well off toward the north, our main trough in the upper levels well off toward the north up here with our surface low coinciding with that trough. A cold front sagging down from that surface low into the southern plains, kind of a secondary surface low developing along that frontal zone, and a sort of warm, nice, warm, moist sector out ahead of that, east of kind of that dry line sort of triple point feature there. And when you tend to get tornadoes in these events out ahead of that surface low, as we saw here in the Joplin vicinity with this event. But again, this was not isolated, this kind of setup not isolated to just the Joplin event. He actually denoted several different events here that kind of had the same characteristics to it. And a couple of those you may have heard of here. The first one is the infamous May 31st, 2013 Reno, Oklahoma tornado that unfortunately killed storm chaser Tim Samaras and his crew, Carl Young and his son, Paul Samaras. So, of course, you've heard of the El Reno tornado, and I'm not going to do a full breakdown of these events. I do plan on doing an El Reno breakdown, as well as our second example, a full kind of case study in the future. But for now, we'll just look at the sort of overall surface pattern here with these events to show you how similar it was to the Joplin event. So, again, this was the May 31st, 2013 El Reno, Oklahoma tornado. And just like our Joplin event, notice where our 500 millibar trough is here. Located well off to the north, up in here, centered right over the Dakotas. As we go on in time here, you can see it doesn't move a whole lot. It just kind of meanders out to the east, belt of flow, rounding the base of that trough. And we're kind of removed from that trough, that main trough down here in Oklahoma. And you can see if we follow this 5820 contour here, notice that it doesn't change its position a whole lot throughout the day here. Very sort of neutral heights here across the region. And again, that we want to see heights falling for a more substantial sort of risk of storms initiating in a given environment. So we had neutral heights down here across central Oklahoma, kind of removed from the main sort of trough well off toward the north. Let's go to our surface pattern here. We go through with time here, so you can see this is at 20Z here. Nice wrapped up surface low up there in the Dakotas right there. Surface cold front extending out ahead of that. leading down into kind of western Oklahoma. Secondary surface low is well developed down here in northwest Texas. And we have a nice warm sector out ahead of that. We'll take a look at this is at 21Z on the 31st here, so our cold front, you can see our wind shift here, winds out of the west here in central Kansas, out of the south here across southeast Kansas into Oklahoma. So our cold front, it's kind of right in here. Surface low, secondary surface low, down in here, kind of in the Childress, Texas area. And we had a nice sort of dry line kind of bulge right in here across western Oklahoma. You can see 100 over 60 here at Hobart, Oklahoma, 93 over 72 here at Fort Sill / Lawton there. So moisture feeding up into kind of that surface low there. And we had a nice, perhaps a little bit of a frontal low out in here as well. But this area right out ahead of that triple point, well removed from the trough, remember, in an area of neutral height rises that was going to be favorable for supercell development out there in kind of northwest to central Oklahoma. And that's exactly what we had happen on El Reno. Here's that environment. Very strong instability as well, similar to the Joplin case. This is at 18Z, mixed layer cape of 3,600 joules per kilogram there. A hodograph that was favorable for supercells here. Nice curvature in the low levels. Lots of streamwise vorticity there. Once again, more of a clustered sort of mode here. Maybe, mid-level kind of storm relative outflow, kind of weak relative storm motion. So that may have kind of created the HP nature of the El Reno supercell as well. Once again, you can see, just a quick aside here, notice the elevated mixed layer here, kind of capping the atmosphere. Notice what happens to it by 0Z. You can see by 0Z, not much happens to it. I do think if we were to pull a wrap sounding out here ahead of closer to the El Reno storm, we may have gotten a little bit less of a cap there. But notice that the low-level wind profile had substantially increased out ahead of that storm. Ample low-level curvature in that hodograph. Similar storm mode to the Joplin case here. You can see as the radar, as we go on with time here, you can see storms fire to the north along the main cold front there, and we get semi-discrete supercells to fire there just ahead of that triple point there in western Oklahoma, where low-level shear and sort of lift was maximized there. We did get more of a clustered sort of storm mode here with the El Reno event. Very, very similar to the Joplin event. You can see storm mergers going on here as well. If we go back in time here, notice that we have kind of our main supercell going on off to the north here, secondary storm down here to the south, and that kind of produces a merger there, right there, and then we get our El Reno supercell to take over. Tornado genesis occurs, and the rest was history. We get one dominant supercell there. Slightly HP mode, high precipitation mode favored there, and also we had, very similar to the Joplin case, sort of other kind of secondary storms kind of raining into the hook area of the supercell here, especially with time. You can see the mesocyclone of the El Reno supercell there. Lots of storms firing behind it and kind of raining into that mesocyclone area with that storm as well. So El Reno, very similar to the Joplin case. Another case from that same 2013 season was the infamous Moore, Oklahoma tornado, the EF-5 that occurred in Moore on May 20th, 2013. Very similar situation here. Here's our 500 millibar trough. Here's Oklahoma City area. Trough well off toward the north here, across the Nebraska, South Dakota border there. Belt of flow rounding the base of that. And once again, sort of kind of neutral heights here, even some maybe slight height rises there across the central Oklahoma vicinity throughout the day there. So large-scale forcing for ascent was kind of nebulous, but if we look at our surface features here, and this case did have some remnant outflow boundary impacts from previous night's convection here, but notice the overall surface pattern. Surface low up here in the Dakotas, trailing cold front out here across the central plains down into a secondary surface low here across northwest Texas. Almost the exact same setup as the El Reno case, very similar to the Joplin case as well. If we look at our surface data here, this is at 18Z, so right about as the tornado was ongoing. So we can see our cold front here. Let's try to pick that out. You can see southerly winds out here across southeast Kansas, southwesterly winds out here to the west. So cold front probably somewhere in here if I had to put a kind of location on it here. Dry line leading up into that. You can see 70s dew points here across central Oklahoma, much less to the south. Surface low out here across northwest Texas. Kind of a triple point forming there in kind of west central Oklahoma, enhancing low-level shear, enhancing lift, and if you have a boundary in play like we did this day, that is only going to further enhance low-level shear. And that was exactly what happened across the Oklahoma City area that day. Here is our Norman sounding from 17Z. Once again, very strong elevated mixed layer above a nice deep moist layer there at the surface. Ample instability here already by midday, 3,000 joules per kilogram of mixed layer CAPE. Shear profile favorable for tornadic supercells here in an extreme. Now, not as much low-level shear to deal with here with the Moore case, but given extreme instability, that low-level shear was going to be stretched into the vertical very, very efficiently. A little bit stronger storm relative outflow here. A little bit of a difference between those mid and upper level winds relative to the position of the storm motion vector there. So a little bit less of a high precipitation mode favored here. Very promising environment for supercell storms, a little bit less of a high precipitation mode. And as a result, we got a sort of a more cellular, more discrete storm mode here. You can see multiple discrete supercells there firing along that kind of cold front ahead of the surface low, ahead of that triple point there. You can actually almost see the triple point there here on the radar. And storms are firing right out there just to the west of the Oklahoma City area. A little bit more of a cellular storm mode, less clustered, and we got a pretty rapidly intensifying supercell there moving into the Moore area, which produced that EF-5 tornado. So you can see even more clearly there. Here's the dry line. Here's our frontal zone. Perfect triple point there showing up on the TDWR radar there at Will Rogers Airport in Oklahoma City. And just a textbook tornado-producing supercell there. One thing to note as well, if we go back in time, notice these showers down here moving up into the supercell. Not 100% sure if these had anything to do with the intensification of the Moore tornado. I think it was already well on its way to being a significant tornado producer, but something to note as well. So that's going to wrap things up here for this Joplin case study. I hope you learned something from this case study. This is a very similar environment to what we've seen in the past with several significant tornado events. So if you see this kind of environment, that secondary surface low / triple point there well to the south of the main trough and surface low up to the north, always keep your eye out, especially when there's ample instability and low-level shear to deal with, as we can get a case as potent and as impactful as the Joplin case. So with that, thanks for watching. We will see you in the next video.